Year 13 Revision Video 3. This video will feature 4 different exam questions on differentiation, integration, trigonometry and parametric equations. Of course, some of the topics may be interlinked between the questions as well. So we start off with a really nice differentiation question. Now effectively we are going to use the chain rule, and if you want to do this using the long format of the chain rule, this is where you would have to set up u equals 3x squared plus 5 and then set up y equals u to the power of 4 and follow through the whole process like that. I'm going to do this using the quick chain rule. So my dy by dx, I need to multiply by the power. So look at the current power, it's 4. I need to multiply by this power, and then I need to reduce this power by 1, so it drops down to 3. And then I need to multiply by the derivative of the inner function here, which is 6x. And this gives me 24x, 3x squared plus 5, all to the power of 3. Now, if you had done this using the long format of the chain rule, you would have had to set up du by dx is 6x, dy by du is 4u to the power of 3, and then dy by dx is the product of dy by du and du by dx, so these two blue derivatives, which is 24xu cubed, but of course you need to substitute back in for u, which is 3x squared plus 5, and you end up with exactly the same answer. But look how much more work you have to do on the right hand side compared with using the quick chain rule on the left hand side. Now we're moving on to an integration question, which has quite a lot of features here. We've got to find this integral, and we're told we can use the substitution u equals 1 plus root x. So for part 1, let's focus on this to begin with. U equals 1 plus root x, or 1 plus x to the half. So du by dx is equal to a half x to the negative a half, which then tells us that dx is equal to, and actually I'm going to take a few stages to do my rearrangement here. So du by dx is equal to 1 over 2x to the power of a half, just rewriting the power on the right hand side, and then 2x to the power of a half du is equal to dx, doing some fake cross multiplying here. So now my integral of x over 1 plus root x dx is going to become an integral of x over, and then of course in place of 1 plus root x I'm going to put u, and then in place of dx I'm going to put in 2x to the half du. Now we cannot at this moment complete this integral because it features a mixture of x and u, so we have to do something about this. So go back to the beginning, and we know that u equals 1 plus x to the power of a half. So this tells me that x to the power of a half is equal to u minus 1, and then x must be equal to u minus 1 all squared. So I'm going to now go back to my integral, and in place of the x here, first of all, I'm going to place u minus 1 squared. Now there's a factor of 2 here, which I'm just going to pull outside of the integral like that. And we've then got this part, which is x to the power of a half, which I'm going to replace with u minus 1. Now the whole thing is over u and is integrated with respect to u. So we now have to work out how to complete this integral. We need to expand the brackets in the numerator, so the brackets simplify to u minus 1 to the power of 3, then divide by u, and then complete the integral. So we need to make sure we can expand u minus 1 all cubed, so you can do this as a triple bracket expansion, or you can do this using the binomial distribution. I'm not going to go through all of the steps here, but you end up with u cubed minus 3u squared plus 3u minus 1. So we have in our integral 2 the integral of u cubed minus 3u squared plus 3u minus 1 all over u with respect to u. And then let's simplify everything. So this becomes the integral of u squared minus 3u plus 3 minus 1 over u with respect to u. So now we have to carry out our integral, and I'm also going to simultaneously multiply by the 2 at the front here as well. So for my first term, I'll end up with 2u cubed over 3. My second term, I'll end up with 3u squared. We would divide by 2, but it cancels with the 2 here. We'll then end up with 6u, and then minus 2 ln mod u plus c. And of course, I'm going to finish this off by replacing u with what it is in terms of x. So that's 2/3 1 plus root x all cubed, minus 3 1 plus root x all squared, plus 6 1 plus root x, minus 2 ln 1 plus root x modulus of plus c. Now let's move on to part 2 of the question here. So we have then got to substitute in some limits here, which we can either substitute limits into the second version of the integral here, the result here, which would mean we have to substitute in our limits as x as 0 and 1, or we can substitute limits in the format of u into this result up here. I am actually going to change my limits from x to u. So if x is equal to 0, which is the lower limit, u simply equals 1. And if x is equal to 1, which is the upper limit, then u is equal to 1 plus the root of 1, which is 2. And what I'm going to do is I'm going to take this result here in terms of u, and I'm going to set in an upper limit of u equals 2 and a lower limit of u equals 1, as I think that's going to be easier than trying to substitute into this result here in terms of x. So this gives me 2/3 multiplied by 8 minus 3 multiplied by 4 plus 12 minus 2 ln 2, and we subtract from that 2/3 minus 3 plus 6 minus 0 because ln 1 is 0. We can then simplify this, which gives me 5 over 3 minus 2 ln 2, and I'm just going to rewrite this as 5/3 minus ln 4 so that I get the answer into this format here, and I can see that my constant a is 5/3 and my constant b is 4. So onwards to our next question, which is about trigonometry. Now, part A. Right, cos squared x in terms of cos 2x. So you should know that there is an identity that tells you cos 2x is 2 cos squared x minus 1, which of course can then be rearranged to say that cos squared x is equivalent to a half of cos 2x plus 1. Now, part B. This is a very standard result. Express the sum of a sine and cosine function as a single cosine function. Notice we are working in radians here. So we want to say that 6 sine 2x plus 8 cos 2x can be expressed in the format r cos 2x minus theta. So we now want to make sure we use the compound angle formula for cos of a plus b here and multiply both parts of that by r. So we want r cos 2x cos theta plus r sine 2x sine theta. Now, let's look at the parts of this that feature sine 2x. We know that on the left-hand side we've got 6 as a coefficient, and on the right-hand side we've got r sine theta. We'll call that equation 1. Let's now also make sure we look at the parts that feature cos 2x. So on the left we've got 8, and on the right we've got r cos theta, and that's equation number 2. So what next? Well, we're going to do equation 1 divided by equation 2, which gives us 6/8 is equal to r sine theta over r cos theta, which of course is just tan theta because the r cancels, and sine theta over cos theta is tan theta. We can work out theta from here, and it comes to 0.6435 ... so 0.644 radians to 3 significant figures, which is of course between 0 and pi by 2 radians. So we then need to work out r, which we can do by substituting back into equation 1 or 2. If you're going to do that, use the full calculator accuracy, store it in a calculator memory and do that. Or simply, we know that 6 squared plus 8 squared will be r squared sine squared theta plus r squared cos squared theta, which is just r squared because sine squared plus cos squared is 1. So this gives you r squared equals 100, r is equal to 10, and this means we can rewrite our original function in the format 10 cos 2x minus 0.644 radians, where the angle theta has been rounded to 3 significant figures. So now part C says hence, which means that this is going to involve parts of the earlier question. The equation 6 sine 2x, that seems familiar, plus 16 cos squared x equals 13 for values of x between 0 and 2 pi, giving our answers correct to 3SF. Now, 6 sine 2x I'm going to leave alone, but I'm going to take 16 cos squared x, and I'm going to use the identity that we wrote down earlier for cos squared x, where we wrote down that cos squared x was equivalent to 1/2 bracket cos 2x plus 1 close bracket. So that was the very first part of the whole question, and this is then equal to 13. So what does the left-hand side simplify to? 6 sine 2x plus 8 cos 2x plus 8 equals 13. And this should look very familiar because we rewrote 6 sine 2x plus 8 cos 2x in the format 10 cos 2x minus 0.644 radians, and then let's subtract 8 from both sides so it's equal to 5. Divide both sides by 10, so we're now solving the equation cos bracket 2x minus 0.644 radians equals 0.5, and we're then going to work out all the possible values for x. Now, note that there is a 2x here, which means ultimately answers will be divided by 2, and this doubles the frequency, so we're going to have 4 answers potentially rather than just 2 answers. So I'm going to find all the answers that fall within range. So we're going to do cos to the minus 1 of 0.5, and we're going to get all of the values. So the first value that comes up on the calculator is of course 1/3 of pi. But minus 1/3 of pi would also work. So think about the symmetry of the cosine graph and what it looks like. Symmetrical about the y-axis, so cos of minus 1/3 of pi is also 1/2. And the reason I'm including that is because when we solve to actually find x, we're adding the 0.644, then dividing by 2, so it's possible this could lead to an answer. We've then got 1/3 of pi, we've then got 5/3 of pi, and we've then got 7/3 pi. So we've got 4 values here, and we're going to see whether these lead to answers. So I'm going to set up 2x minus 0.644 radians equals minus 1/3 pi, and I'm going to see what value of x this results in. Notice I'm using my full accuracy here because I've stored this value in a calculator. Now this actually gives me x equals negative 0.201, so actually it is out of range, so we don't really need this answer here, but it was useful to have actually checked it. I then have 2x minus my angle theta equals 1/3 of pi, and this gives me x equals 0.8453 ... So that's 0.845 to 3SF. I then have 2x minus 0.644 equals 5/3 pi, and this gives me x equals 2.9397 ... and that gives me 2.94 to 3SF, and I'm going to keep going. So I've done that one and I've done that one. So 2x minus 0.644 equals 7 pi by 3, and that gives me x equals 3.986 ... so 3.99 to 3SF. So that's only 3 answers so far because this one didn't work. And I'm going to check the next angle after 7/3 of pi, which is a result of cos minus 1 of 0.5. And that's going to be 4 pi take away pi by 3, which is 11 pi by 3. So 2x minus 0.644 equals 11 pi by 3. This gives me a value of x, which is 6.0813, which is 6.08 to 3SF, which falls within the range 0 to 2 pi, because 2 pi is approximately 6.28 radians. So on to the final question in this question set, which is about parametric equations. And these parametric equations are defined below. X equals tan theta, y equals 1 plus cos 2 theta, and they're defined across theta equals theta between 0 and pi, but theta not equal to pi by 2. So part 1, explain why theta can't be pi by 2. Well, it goes straight away to here, and we can see that tan theta is undefined for theta equals pi by 2, so x is undefined for this value. So that's why we disallow theta equals pi by 2. Now, part 2, show that the maximum value of y for points on the curve is 2. Well, y equals 1 plus cos 2 theta. We know that the cosine function here takes a maximum value of 1. Doesn't matter that there's a 2 theta there, that just alters the frequency, not the amplitude. So cos 2 theta has a maximum value of 1, which means that the maximum y value is 1 plus 1, or 2. Right, part 3, show that the Cartesian equation of the curve is given by this result here. Now we could aim to eliminate theta between these equations and show that we get the result given there, the Cartesian result. Or, because it just says that show that this is the Cartesian of the equation of the curve, we could substitute in the x values and show that we end up with the y value as appropriate. So what I'm going to do is substitute in x into this Cartesian equation in terms of theta. So instead of x squared, I've got tan squared theta, and I'm going to try and aim to simplify it and show that I end up with this result over here, the y result. So the denominator is currently 1 plus tan squared theta, but we should know that that is equivalent to sec squared theta. Knowing our trigonometric identities, we know that 1 plus tan squared theta is equivalent to sec squared theta. And we know that sec theta is 1 over cos theta, which means that this is the same as 2 cos squared theta. Now, we know that there are identities that link cos 2 theta and cos squared theta, and in particular cos 2 theta is 2 cos squared theta minus 1, which tells us that 2 cos squared theta is the same as cos 2 theta plus 1. So that's why. So that then shows our result. There are other ways of doing this. This is a nice, simple way of getting to the answer we wanted, or verifying that the Cartesian equation is correct. And then the last part of the question says that the point P in the first quadrant lies on the curve. Find the coordinates of P given that OP is the normal to the curve at P. So we really need to do some differentiation here. If we're talking about normals, we're talking about normal gradients, we need to know what dy by dx is. So x is equal to tan theta, y is equal to 1 plus cos 2 theta, but we also have the Cartesian equation, which we've been given for clearly some good reason, and that tells us that y is equal to 2 over 1 plus x squared. And we can differentiate this to work out dy by dx. I'm going to actually differentiate this using the chain rule, so I'm going to rewrite it in this format here. So rather than using the quotient rule, I'll use the chain rule. Now, it's a power function, so I need to multiply by the power, so this becomes -2. I reduce the overall power by 1, so this becomes a power of -2, and I multiply by the derivative of the inner function, which is 2x. So tidying this up a little bit, this gives me minus 4x over 1 plus x squared all to the power of 2. That's our dy by dx. Now, what do we know about the point P? Well, let's say P has coordinates x, y. Then the gradient OP is equal to change in y from 0 to p, which is y, over the change in x from 0 to p, which is x. Imagine a right angle triangle here. The gradient of OP is y over x. Now, OP is a normal, which means that if we drew the tangent to the curve, the gradient of OP multiplied by the gradient of the tangent would equal -1. So y over x, which is the gradient of the normal, multiplied by this gradient here, which is the gradient of the curve, or the gradient of the tangent to the curve, must equal -1. And we end up with an equation that simplifies a little bit. You can see that x cancels from here and here. And y, of course, can be rewritten as this. So I've got 2 over 1 plus x squared multiplied by -4 over 1 plus x squared all squared equals -1. And let's keep simplifying this. So that's -8 equals -1 plus x squared all to the power of 3. Or 1 plus x squared all to the power of 3 equals 8. And rather than expanding, I'm going to take the cube root of both sides, which tells me that 1 plus x squared must be equal to 2, x squared must be equal to 1, x in theory could equal 1 or positive 1 or -1, but I'm going to say x equals 1 because from the diagram you can see that at P, x is clearly a positive number, so x is equal to 1. Y can then be calculated by substituting into the equation here. So y is equal to 2 over 1 plus 1 squared, or 2. So y equals 1 as well. So it has coordinates 1, 1.